So we have a few different elementary potential flows, and now we can combine those and create a more complex flow field. So we're going to look at flow over a circular cylinder, which we're going to find is a really important flow to understand. And we keep calling it a circular cylinder instead of just a cylinder because we're going to look at different types of cylinders. Not all of them will be circular. So right now we're just looking at a circular cylinder. And in the past, we've found that we can model this flow as the free stream plus a doublet. Oh, and I actually drew that sideways. Let me fix that. Okay, plus a doublet plus a vortex. Okay, and when we add all those together, what we get is flow over a cylinder with circulation. Now we can set gamma, which is the strength of that vortex, we can set that to 0 and get just flow over cylinder without circulation. Kappa is the strength of that doublet, and V infinity is the strength of the free stream velocity. And so when we add all those together, we'll get some flow that goes over the cylinder like this, and we'll find that the radius of the cylinder is actually a streamline, and that we can find a stagnation point on the leading edge and the trailing edge. And of course, if gamma is strong enough, well, as it gets stronger, the stagnation points come together here near the bottom for positive gamma, and then if they get strong enough, then that stagnation point can actually exit the surface of that cylinder. But anyway, this represents flow over a circular cylinder or a lifting cylinder if gamma is non-zero. Okay, so we can now come up with a capital phi for this flow field, and it's simply the summation of all of our capital phis for these three different potential flows, or elementary potential flows. Now, to simplify this, I'm just going to say that alpha is 0 for the free stream, so that's going to go to 1, and sine of alpha will go to 0 if alpha equals 0. So that's just to simplify this, but we could leave it in there. And so what we'll get now is from that first term, we get V infinity times Z. And then all of these, so we see that we've got that first term in there. This term is 0. And then all of the complex constants, we're just going to combine into a single constant here at the end. So we'll put that there later. So the next term here is plus I times gamma over 2 pi natural log of Z. So that's from our vortex. And then we can add the term from our doublet, which is kappa over 2 pi 1 over Z, and then plus our complex complex constant out there. Okay, now one thing we found with kappa is that kappa is related to the radius of the cylinder, or maybe I should say the radius of the cylinder is related to the relationship between kappa and V infinity. So we found before that kappa we could write as 2 pi r squared times V infinity. And so we would swap out kappa for the radius of the circle, or the circular cylinder that we're looking at. And then we could later back out the strength of kappa, but this then makes capital R an independent variable that we can choose. And then we could simply solve for kappa based off of our free stream velocity. So those three terms are related. So we're going to swap out kappa for capital R. And so what we get here is we're going to combine the because we've got a v infinity here, that's now going to be in this term. So we're going to combine those two terms, and what we're going to get is v infinity times z plus r squared over z. And then the imaginary term here is I times gamma over 2 pi natural log of z. And then we've got our complex constant. Okay, so that's our final version of capital phi for this case of flow over a circular cylinder with circulation, and where we've set alpha equal to 0. Now we can take the derivative of that just like we did before. So wz is simply the derivative of phi with respect to z. And we get v infinity, derivative of that first term is 1. And then we've got a z in the denominator, so the derivative of that next term is going to be minus r squared over z squared. Okay, and then plus I times gamma over 2 pi. And then the derivative of natural log of z is simply 1 over z, and the derivative of that constant is 0. So this is our final potential, complex potential and complex velocity for flow over a circular cylinder.